Hi, you guys can hear me, right?
Yep.
Okay. I can pin it to myself. And before we get started, oh, I don't have my video on. Now I do. Now I have my pencil down here. Okay, before I get started, your homework is due on Monday. And I did just post all of those handwritten notes that I've been collecting over the last several weeks. And I posted some notes on advection dispersion too. So we'll finish up plug flow systems today. Hopefully, maybe not, but we should be able to get through it. And then I may start a little bit on dispersive systems. I think we're ahead. I haven't looked at let me look at the calendar. Today is the 26th of March, so we have 1, 2, 3, 4, 5 weeks left after, and then an exam week. And we're not going to have a final exam in this class because it's only going to be homework. So on Monday, I'll give you your next homework assignment. And you'll probably have 3 more homework assignments because one of your homework assignments will be due during probably during exam week, because we'll talk about it up through dead week, and then it'll be, rather than a final exam, you'll have a homework assignment due exam week. So I think I can give you at least 3 more homework assignments. And so before I start going over the notes again, I want to know if you have, and let me look at the chat box to see if anybody's if anybody has any questions about the current homework assignment. Nobody? Everybody's okay with it? I think I went over it well enough that you shouldn't have too much trouble with it. Let me, I still have Chuck Mangione up here, and I still have WebEx. I don't need this anymore. Let me go to here. So if you go to Brightspace, there's Course Home. I haven't written any announcements here for a while, except for this. I think Shruti wrote this correction on homework 4. But if you go to content, I haven't posted anything for a while because the notes on plug flow systems are quite long. But if you page down here, here is in N12 streams, which is what we're going over right now. I just posted these, which are all of those notes that are handwritten. And I went back a ways, so there's 16 pages of handwritten notes here that I wrote while I was lecturing. And most of these, the concepts are in the regular notes too, but I've gone over some of the homework problems here and added some of those. But you got 16 pages of these notes that you can go back and refer to if you get confused too. Let's go back to this then. And then I have uploaded some down here, wherever it is, N16. This is N12, this is 16. That's because I've got 13, 14, and 15, which I'm gonna upload later. but I thought I would change the order because this is dispersive systems, which are, I typically don't go over this in this class. And since you don't have to know this for any exams, there's just a few simple concepts in here I want you to understand about dispersive systems. I go over how to model estuaries in these N16 notes a little bit. But it's actually useful because when we start talking about groundwater systems, if you understand advective dispersive flow, then you understand, then it's easier to just add on adsorption to it. So you understand advective dispersive flow with adsorption as occurs in a groundwater system where you've got a solid media that chemicals can absorb to. So we'll go over dispersive systems first before we go over groundwater systems. But I'm not going to go through these notes very thoroughly. I'll just point out some highlights in these notes. So we're still on N12 streams, and I have those down here in a PDF, so I'm just going to put them up here. The other thing I could potentially go over, this page right here in N12 is actually MathCAD. I don't know if you use MathCAD in any of your other classes. And I can't see the chat box. So does anybody in this class use not MATLAB, but MathCAD? Does anybody use MathCAD? Oh, I see a message came up. Matthew said nope. Anybody use it? No, nobody's used MathCAD. MathCAD is quite useful, and it's on Purdue's Go Remote software, so you can always access it. And they use it in a few classes in ABE, I believe. They used to use it in civil engineering. I'm not sure if they still do, but it's very, very useful. I actually like it, and as a student, you can buy a software version of it for, it used to be $10, now it's like $100. But it's very useful, especially if you want to use it for like calculus and math classes, because you can check your homework, because it'll integrate and do differentials and everything else. So if we have the last week of class, if we've got some time, I'll show you how to use MathCAD too. Some students really like it, some students hate it because it's just one more thing to learn. But it actually is quite powerful. And what I've done here is, for this problem, I've solved the Streeter-Phillips equation because we've got A, B, and C. B is our deficit. And so you can see the deficit goes up and then goes down. This first curve is the BOD line. This is the dissolved oxygen deficit line. And then this is I'm not sure what this is. It's not oxygen. It's the last thing, which is the reaeration formula, but I'm not quite sure what we did here. So it's actually shows you how to solve 3 ordinary differential equations in MathCAD, because you can do this in a given loop. You can go to this ODE solver, send it the ODE solver, send it the time, where you want to print it out and everything else. It's very easy to solve ordinary differential equations in things like MathCAD. You can also solve ordinary differential equations in MATLAB, because as I showed you before, there's several built-in software packages in MATLAB that allow you to solve systems of ordinary differential equations. So this is like at the very end of these notes. So let's go up here and we'll talk about the rest of these notes. Okay. We were about to this point where, again, this is the oxygen profile in our stream. This is a deficit profile in our stream. And this would occur below a sewage outfall where the treatment plant is not working properly. And this is why we build wastewater treatment plants, is to not have this oxygen sag downstream from plants. We solve for the critical deficit here, because the critical deficit is, if you're going to get fish kills, it's going to occur at that point in the stream. And that point in the stream is, this could be 20 kilometers downstream. So it could be over a couple kilometer reach that you have an oxygen deficit that's low enough to cause fish kills. We talked about critical conditions, and the last thing I showed you last time was this paper that one of Professor Nyes and my PhD students did on the Wabash River. And I showed you that in the summertime you get very, very low stream flow. So in the Midwest, hey, in the middle of the summer, the water is evapotranspirated very effectively. We get a little bit of rain. We get lots of rain this time of year. As you know, yesterday we got a ton of rain. We don't get those kinds of rains in August typically. They're springtime rains. So the worst case for the deficit is summertime, where the temperatures are high, which means these rate constants are high. KD is very high because biological activity is high. So that means it drives the deficit down faster because the microorganisms are growing faster because they're warmer. And then that means that you could have a lower deficit here because you don't get enough reaeration in that stretch. So the critical conditions, there's a critical deficit, but there's also critical conditions, which are generally considered as low flow conditions with maximum temperature. So summertime, hot temperatures, low flow. So summertime, maximum temperature conditions and low flow are basically the two things. Winter with ice, you get no reaeration, so you can get oxygen deficits in the winter time too. But typically those don't happen too often. And change in flow conditions. Obviously this point moves as the flow conditions change. And I went over this last time. There's the PDF page of all of these reaeration formulas that you can use to actually calculate the reaeration rate. The maximum deficit, remember here, this is a common term, L naught equals W over Q, because W is the waste load. So think of W as a waste load. I don't know if I even wrote it here, but I've written the same thing here too, but I don't think I've defined W. You can figure it out because you know L naught is BOD, milligrams per liter. Q is flow, which means it's liters per day. So you can calculate W as being milligrams per day, because this has liters, this has liters. They cancel, this has milligrams, this has per time. So you have a milligrams per time in this W. That's a waste load. In other words, how much BOD per time are you discharging to the stream? So how do you calculate L naught? Well, you take the total flow of the river, which includes the flow coming from upstream, plus the flow coming from the plant. And then if you know how many milligrams per day are being discharged, you can calculate the BOD at X equals 0 within the stream. So as L naught increases, the maximum deficit increases too, because the more BOD you put in the stream, the more BOD is utilized, and you get a larger oxygen sag. You can see that from the equation. Higher change in oxygen with distance as you go up in L. So it just makes sense. Hey, you throw more waste in the stream, you're going to end up with a higher oxygen deficit. But this is a waste load, which again has units of milligrams per time. In dams, that you get decreased Q, decreased velocity. You get a increase in height, and so the overall reaeration rate decreases. In lakes or behind dams, you generally have a reservoir or a lake, but since it's a man-made dam, it's called a reservoir because, hey, it's man-made. So a reservoir is a man-made lake, right? You get a decreased reaeration in those cases, but you also get suspended solids falling out. So you typically don't have particles that are causing oxygen depletion like you do in a moving stream. So you got lots of effects because of dams and streams. You can have an initial deficit, and this is the whole idea behind waste load allocation, is you have a plant upstream that creates a deficit. Now you're discharging more BOD at this point, so it's cumulative. At this point, then, that means that you have an initial deficit, and from this point on, you have to model again, and your deficit curve won't be the classic deficit curve, which goes up and then back down. It stays up because you've got this initial deficit coming in from upstream, and then you get a deficit curve going down, which is accumulation because of the waste discharged upstream and the waste that's discharged at this point. So in all of these models that I was showing you the other day, like Quali 2, it accounts for multiple discharges to the streams, and you model then sections of the river at a time, and then you can model where the rivers join, where tributaries come in and everything else. So you can model the whole river, you know, with its tributaries and everything else. Large deficit, you will not see a typical oxygen sag curve because, hey, from this point on, it goes like this. Overall, you might, because if there was a waste coming in up here, it started to sag, well, it's just going to stay down for a lot longer if you got a new waste coming in here. Limitations to the Streeter-Phelps equation. Point sources only are treated. It doesn't account for non-point sources. Non-point sources right now are a real issue with phosphorus loads into the Great Lakes, which are causing these green algae blooms. It only considers carbonaceous BOD. It doesn't consider nitrogenous BOD. And remember, we talked about this the other day because when we talked about Qual 2E here, we have the BOD here, dissolved oxygen, being consumed by carbonaceous BOD, but this Qual 2E model also has a nitrogenous component over here. It's got the organic nitrogen being converted to ammonia, being converted to nitrite, being converted to nitrate, and then those are uptaken by algae, and algae produces and consumes dissolved oxygen a whole bit. So in more complex models, you have these terms incorporated into them too, and they do consider the nitrogenous BOD, not the simple carbonaceous BOD. Okay, but Streeter-Phelps, the original model, hey, just carbonaceous BOD. Where am I here now? I gotta go way up here again. Sorry about this. We're all getting headaches by now. Only reaerations consider no photosynthesis, so it doesn't include algae. And there are models now that include algae because algae is important in a lot of streams, especially in the summertime with low flow conditions, because the algae is allowed to grow over the time period that the water's in the stream, and you end up with green rivers in the summertime often, which at nighttime can be problematic because at nighttime those algae are consuming oxygen and driving down the oxygen concentration. So oftentimes in the summer, if you have lots of algae in the stream, you don't notice fish dying until you come come out in the morning and all of the fish are dead because they died overnight because there was no oxygen in the stream at nighttime. Because during the day you can get super saturated oxygen concentrations. If you've got lots of algae, they produce oxygen, and instead of having 8 to 10 milligrams per liter of oxygen, you can have 16, 17 milligrams per liter oxygen in the water because it's being produced by the algae and dissolving in the water, and then it's fluxing out into the atmosphere because the water's super saturated with oxygen. It's fluxing out, just like CO2 fluxes out of a Coke bottle once you open the cap because it's super saturated with CO2. Okay, no mixing up or downstream. It assumes it's completely mixed laterally and with depth. It's basically a plug flow model, and it's a steady state model because it assumes that at one point along the stream you're having an input of waste of BOD, L, and then that L is being consumed as it moves downstream, depleting the oxygen concentration. So it assumes steady state, steady flow, steady cross-sectional area. All of the things are constant in the model, and it assumes even steady state that the dissolved oxygen concentration in time at any point along the stream is the same. BOD first order assumes first order, and we know that if we add more bacteria to the stream, we're going to get a faster rate constant. So it doesn't include bacterial growth and decay or any complex factors for BOD utilization. It just assumes it's a first order process. And BOD measurements in general do not account for bugs. I say bugs here, but bacteria, because we know that you increase the bacterial population, you increase consumption. You know, you put 2 people around a pizza, it may take 10 minutes before it's gone. You put 10 people around a pizza, it's gone in a minute. That's basically what this sentence is saying, right? The more bugs, the faster the utilization occurs. Other sources and sinks. This is actually an important concept, this equation. Accumulation equals inputs minus outputs plus or minus reactions. This is our basic mass balance expression, where accumulation is mass per time. We have, and I brought the V in here, V times D, the volume of our control volume times the deficit over the change in time. I brought back the differential equation in time. Inputs, Q times D minus Q times D plus delta D. So going back to how we described this initial plug flow system, this is inputs, this is outputs. Remember, way up here we did this. We have inputs, outputs, plus or minus these 2 reactions. So to develop the Streeter-Phelps equation, we only had these 2 reactions. BOD decaying, producing deficit, right? In other words, this, for every one of these that happens, we get an increase in deficit. But the deficit is reaerated away because of oxygen transfer to the stream. So we have 2 reactions here acting on our deficit. And we did this by setting up our little control volume like this. In this case, we would have a D here, a D plus a delta. This should actually not be, this is wrong here. Sorry about that. I don't know why it says plus delta X. It's not plus delta X. It's plus delta L. I think it didn't come out right when it got copied, but it's L plus delta L, not delta X. I mean, that's silly, and you know that. Because just like we did up here, right, when we did streams, way at the beginning we did the stream, and we did C plus delta C. So this is the first page of our stream thing. This is concentration, and through our plug flow system, our concentration can change. So coming out of our system is the initial concentration at this point, plus some change in C, which could be either positive or negative, depending upon what is coming in up from down here and what these reactions are. Because we could have a higher concentration coming in, which means our concentration profile is, we're on the increasing concentration as the flow is coming down, or we're on the tail end of the peak where the concentration upstream is lower, and so this would be a negative change in concentration. Change in concentration is decreasing with time. But then the reactions, if they're negative, we will get a decreased concentration, change in concentration here. And if they're positive, we get an increase in concentration here. So we have the output term. This is our output term. So we have a Q times D plus change in D. That's all we've done. And then we've got the two reaction terms for our Streeter-Phelps equation. Okay, so I don't know why. I don't think I ever caught that before. Whoops, where am I? I don't think I ever caught that before, that this little box is screwed up. Come on, where is it? Anyway, so here we go. Inputs minus outputs. We have our BOD, again, KD times L times V. We have this term. So we have this term and this term. 1, 2, 3, 4 terms. Those 4 terms are the Streeter-Phelps equation. Other sources and sinks then are everything else that we've added to this. So beyond BOD utilization, this is carbonaceous BOD. We can add nitrogenous, where N is our nitrogen. N is nitrogenous BOD, L is carbonaceous BOD. So we've added a nitrogenous term here. S is sediment uptake. So we have so if you've got sediments, and oftentimes in streams the sediments can be quite mucky because you've got particles settling out. Well, those particles still have an oxygen demand. And they've got such an oxygen demand that sediments below the first centimeter of the sediment, you get anaerobic conditions where you can produce methane gas, and you can have, these really, really mucky sediments. But at the surface, it's still consuming oxygen. So a sink for oxygen is often the sediments, unless it's a nice sandy sediment. If it's a sandy or rocky, gravelly sediment, you're going to have very, very low sediment demand at the bottom of the river. But the oxygen, mixes in the stream. It gets to the interface between the water and the sediment, gets uptaken by particles within the sediment. That's what this term is. And you have to divide by the height, because the higher the water column of the river, the lower the sediment demand over the entire volume of that or column of that water, right? So we divide by H here to normalize it. R is respiration, and this is plants and algae. So when I say plants here, it's also algae. Respiration. Respiration consumes oxygen, so therefore it's a positive term. All 4 of these are positive terms because they're consuming oxygen, increasing deficit. So they're a positive influence on deficit because, when they consume oxygen, they cause a deficit. Because again, the deficit is the saturation value minus the actual value of molecular oxygen in the water. So respiration of algae and other plants, rooted plants, creates a deficit. But then over here we have photosynthesis. So photosynthesis by plants is a negative force, just like reaeration. So we have 2 mechanisms to get oxygen into the water body: reaeration from air and photosynthesis of plants and algae. So these are all processes that are going on within a river. The simple Streeter-Phelps equation only includes input, output, BOD utilization, creating deficit, and reaeration, eliminating deficit. But we've got if we have algae in plants, we've got these two process, or this process and this process. We have highly mucky sediments, we've got this process occurring, and we will always have some nitrogenous demand there too. So we can simplify this again, rearrange it, we get this equation, and you get the idea. There's a, if we do this, yeah, nitrogenous demand, just like BOD, we can substitute it in because we know that the nitrogen breaks down according to, we can assume a first order process of that. If we do that, we get a term that's identical to the BOD. So this is carbonaceous BOD, this is nitrogenous BOD. Sediment is just usually considered a constant process. Respiration and photosynthesis are oftentimes considered constant processes if we want to know an average respiration and photosynthesis. We'll talk about these because these can be diurnal too. But this is linear first order non-homogeneous ordinary differential equation. That means that we can rearrange this, we can bring this term over to this other side, this term over to this other side, and get the D's on this side, and then all of these forcing functions. These forcing functions are additive, which means we can solve for the equation with one of them in, and then solve for the equation with another one in, and then solve for the equation with the other one in. And then we can look at what all of those terms are, and then we can add them together. So if you do that, if you basically use that integration formula and put each of these terms in individually and solve for it, and these three you could add together because they're all constants, right? This is one constant forcing function on this side, like a K. Well, we can plug it into the thing. This is a function of X, this is a function of X, so we have to solve for this independently. We have to solve for this independently. These three we can solve for all together. We get this, and again, solve for them all three together, we get this. So we get the original Streeter-Phelps equation that looks like this. And then the nitrogenous decay, we also have reaeration taking away the nitrogenous decay. So we get a term that looks exactly like the carbonaceous BOD for the nitrogenous demand. And then respiration, sediment deposits, and photosynthesis, they're all additive processes. So depending upon which is bigger, photosynthesis could be bigger than both of these, and then that would mean that it would be a negative to the deficit. You guys get the idea. That this equation right here, even though it looks complex, is quite easy to solve analytically. With one stream, you know, from upstream to downstream, constant coefficients, constant cross-sectional area, inputs at one place, etc. Okay, so we kind of get this, and then but principle of superposition, we just talked about that. Production and respiration, we can make algae and plants respire all of the time, but they don't photosynthesize all of the time. They only photosynthesize when there's sunlight available. So the photosynthesis part of this could be a function of time. And there's some classic papers that have done this as a sine function. So you get diurnal variations in dissolved oxygen in the stream because of this. And so this is just one paper. It's an older paper. Steve Chopra, I think he's still at University of Colorado at Boulder. This is an older paper, 1972, but he's a faculty member there. And he's done a lot on water quality. He's actually got a book out on water quality modeling. You know, he's done some work on these diurnal variations of oxygen in streams. Non-point source, if you consider just a stream with no point source discharges. So let's do this. I'm going to stop sharing for just a minute. I'm going to write this because now we have a stream with flow going this way, and we have L going in all along here, right? So basically, L is utilized, or it's getting into the stream. It goes down, but it's not going down because it's constantly being put in. That means we have a constant L because L is decaying. L is also decaying, but it's constantly being put in. So that means L is constant. L is flat with this, right? Because this is what would happen if we decayed it from this point. But if we're constantly inputting it like this, well, the average of those two is a flat line. That means we have a background deficit because we're constantly inputting L along the stream. So this is non-point source. When we talk about non-point source pollution, it means that you're constantly all along the stream. You've got farm fields and everything else that are all along the stream putting it in. It's not coming in a pipe. It's coming in all along the stream. Okay, that's what a non-point source pollution is. And it's typically because of farms. So I'm going to go back and share this with you. So let's assume our saturation value for dissolved oxygen is 8 milligrams per liter. Assume the water quality standard is 5. We have to maintain 5 milligrams per liter for a water quality standard. And this is true in some streams in Indiana. Assume a background deficit of 1 milligram per liter. That means our safety factor is 1 to 2 for rural, for urban, 2 milligrams per liter. And so if we take a look at our basic equation here, change in deficit over the change in distance times mu is equal to minus Ka times D. This is a background deficit now. We know what our background deficit is. Well, actually, we could calculate because we know what our background BOD is. If we know our background BOD, we can calculate our background deficit. Because our deficit, like I said, our L is not changing with distance. That means our deficit is also not changing with distance because it's constantly being reiterated in, but we always have a background deficit. So if we have a background L, that means we have a background deficit, and it just is a function then of the ratio of KD to Ka. This is not assuming any photosynthetic activity. Again, we've done basically Streeter-Phelps modeling here, where we're just assuming carbonaceous BOD and reaeration. But, so with most rivers, if you didn't have any photosynthesis, you'd always have a low background BOD or a low background deficit in them if you always have this BOD. Although in the summertime, hey, we get these diurnal variations because of algae growth. So it can be super saturated during the day, way undersaturated at nighttime, and then it can come up. I talked about this page. This is MathCAD. I'll show you that sometime. And equations. This is BOD deficit. These are the two equations. This is the Streeter-Phelps equation, right? This is where the critical deficit is. And then I've also added, and we're going to talk about this, salinity, reaeration, estuaries. These equations from salinity on down have to do with estuaries. And so this is the deficit that would occur in an estuary where you have mixing upstream and downstream because of dispersion. So this is dispersive mixing. This is plug flow. So I've given you the equations for estuaries here, but we'll talk about them a little bit more. And then dispersive flux of BOD. So this is all, again, estuaries, and we haven't talked about that yet. And just, this is actually a good exercise. It's 1209, but in that one page, and if I can I can show it to you. The one page in the notes, if I can find it, I've given you, where is it? I gotta look at type. Reaeration formulas. Here it is. I've also given you this sheet, and it has these reaeration formulas. And this first one, Ka equals this, Ka equals this. How do you get from this point to this point? In other words, what are the units on this 12.9? You can basically put this value into here, rearrange this, convert your units and everything else. It takes about a page to get from this formula to this, even though they're essentially the same formula, just with different units. So in the, where did I go now? Where's my sheet? Oh, come on. Yep, there we go. No, I'm trying to do this, and I don't know why. I am sharing my screen. Where is my... It is this one. Here we go. This page actually does that. It goes through it and starts with this equation with the diffusivity coefficient of oxygen in water is 10 to the minus 5 feet squared per hour. These are the units. You plot, you do all of these unit conversions and everything else. If you can follow my craziness there and cancel all of the units, and some of these units are like the 3/2 power, so it takes a while to do this. You get down here to this, where Ka is in per day, flow is in feet per second, and H is in feet. So oftentimes this equation is given in this, and it's odd because you have to plug the value of mu in here in feet per second. You have to plug H in here in feet, and it gives you a Ka that's in per days. Well, how do you know that that's right? Well, this page shows you because it starts with the original equation and just basically goes through all of the unit conversions to get there. So I'm giving you that page. And then the last page is this. So we did finish streams today, and I don't think I'm going to start anything else, but I'm going to stop sharing and see if you guys have any questions. Do you have any questions about anything? Nobody has any questions. Does everybody know where they're going to work this summer? Somebody was starting to ask me a question. Unless that was a nope. Can't find work. So let me share one thing with you. I'm going to share screen one, and I'm going to go to here. And I'm going to search for maps. Google Maps. I do this with all my advisees. Let's say you live in, where do you want to live? Dayton, Ohio, Akron, pick a city, any city. Somebody.
Chicago.
Oh, Chicago's too big. Whereabouts in Chicago? Western suburbs, northern suburbs?
How about West Side?
West side. Let's look in Naperville. Let's look around Naperville. I'm going to Google in here environmental engineering. Engineering. Yeah, engineering. There you go. That's where you find a summer job if you live in Naperville. Golder Associates is huge. There's civil and environmental consultants. There's environmental solutions. Some of these you have to be careful because they're like HVAC, because sometimes they say environmental and they mean environmental homes and your HVAC and all of that stuff. But some of these, like Golder Associates, if you click on it, over here, Golder Associates, here's their webpage. And they have projects all over the place. They have locations, all Europe, Africa, Pacific. About us, let's click on About Us. About Us, how many people? Like a ton. Like, they have employee-owned since the founding 1960, more than 7,500 people operating from 155 worldwide offices. So even if you wanted to go in their office and interview there, you could find out if they've got internships other places, if they don't have them in Naperville, okay? Another place to look is if you Google top 200 environmental firms. There's this journal, ENR, that publishes the list of top 200 environmental firms. For the 2000 or 2020 and recent, you actually have to subscribe to see the whole list. Oh, maybe not. Here's 0 to 100. Let's see if I have to subscribe. Yep, they want me to subscribe. That doesn't matter because I can go back. Here's Tetra Tech, Bechtel. You can Stantec. You can just copy it like this. Copy and then open up a new thing and let's paste it and let's see what Stantec is. There's Stantec. And they've got careers here. I could look for careers at Stantec. Okay, I can look for, see, do they have any internships? These are the, so this is the top 200 environmental firms. So AECOM is the largest, Jacobs is next, Tetra Tech is next. Bechtel was a Purdue graduate. Bechtel really isn't an environmental firm, but they do a ton of environmental work. So he's a construction engineer type person. They build pipelines, but they also build everything. So some of these companies like AECOM do everything. Jacobs got started in environmental. Tetra Tech is known for environmental. Black & Veatch is known for water and wastewater treatment. You get the idea. If you go back to the older ones, like what were the companies in 2014 and on the list, then they actually tell you a little bit more about, I don't know why it opened up this. It 2014, maybe it doesn't have it. Yeah, 2015 it's asking me to log into. But you can get a lot of information from this page. But you can also get a lot of information by going to your hometown and just Googling and seeing who's there. Who's in your backyard that if you wanted to live at home and work for a consulting company, could you do it at? So that's my 5 minutes of explaining how to find an internship over the summer. I hope that's helpful. Oh, can we choose LA? I got 2 minutes, so if you want to leave, you can, but let me look at LA, and you'll be, and LA is interesting. Share content. We'll go back to here, and we'll look in. We'll go to Los Angeles. And you could do, again, you could do Long Beach, you could do any place. And you have to zoom it to different scales. Because if you zoom to this scale and look, you're going to come up with different firms, okay? So there's a whole bunch here. Atlas Environmental, Western Environmental. If we go here, up here, and click on it, we'll find ones that are up here in this area. So there's at least 200 different firms in the Los Angeles sort of area that you can work. Up in San Francisco, there are a ton. San Francisco is expensive, but there's a lot of them that are over here, like in Walnut. Walnut, what is it called? Walnut Creek. So Golder Associates, Haley and Aldrich. These are big companies, and there's some that are in downtown San Francisco, some up here. And again, like I said, if I go out here further, I will and search again. I'll get different, some different ones out here. I guess not too many. Who's this? Okay, you get the idea. So there's a ton of places, and you can just use Google Maps to help you search for places to work. Okay? I'll see you guys on Monday. Oh, looking for full-time jobs, you could do the same thing. But you could also look and see who's hiring based upon, like, go to AWWA and other professional organizations, WEF, and see if they've got job listings for the organizations. So I will do one more thing here, share content. We'll go back to this again. And I'll, rather than do this, I'll go to WEF. And Water Environment Federation, 35,000 membership events, advocacy, become a member, careers, and they may have regular recruits, and they recruit, but they may have a job listing. So they may have a thing, Career Center, browse the openings. Is continuously updated with new employment listings from career for wastewater. But all the other agencies or organizations do this too. So checking with professional agencies, here's employers, post, and you can post your resume here and everything else. You get the idea. So even these professional agencies have clearinghouses for jobs. WEF, AWWA, but the jobs that are going to be listed here are going to be the jobs listed by that top 200 environmental firms. Okay? So you get the idea, I think. And you can look at corporate jobs too, and that's like, hey, could I get a job for Ford Motor Company? You just have to look in their website and see, are they hiring people that do environmental compliance, environmental engineering, environmental science, permitting, things like that. Okay? Okay, I'll see you guys on Monday. So long.